In the last lecture, we learned about Miller compensation, and that by placing a compensation capacitor across the inverting output stage of the two-stage op-amp, we could effectively compensate the op-amp with a relatively small physical capacitor while realizing a much larger capacitance. So after we did this compensation, we ended up with a couple of poles and zeros. So the first thing we saw was that we had a dominant pole whose frequency was given by the following. And what we see here is that we basically have the gain of the second stage multiplied by the resistance from the first stage times the compensation capacitance. We had a second pole that was given by the following. The GM of the second stage times the compensation capacitance divided by capacitance from the first stage times capacitance from the second stage plus the compensation capacitance times the sum of the first and second stage capacitance. Now we expect the compensation capacitance, or the effect of the compensation capacitance, to be larger than both the first and second stage capacitances. And if we do that, then we can approximate this whole thing as GM2 divided by the load capacitance, CL. Finally, the compensation capacitance also brought a right half plane zero into play, and the right half plane zero had a frequency that was equal to GM2 divided by CC. This is problematic because a right half plane zero causes a negative phase shift, and it contributes to potential instability because of that. If we model our op-amp like we did when we were initially analyzing the Miller effect, we treat the first stage like it's simply a GM, and it's driving the output resistance of the first stage and then driving the second stage. Now the second stage we're modeling as a current source biasing a common source amplifier. Now at high frequencies, the compensation capacitor that's placed around this current source is effectively a short circuit. So I've drawn that effective short circuit there. Now if we analyze the voltage gain of this circuit, we would find that it would be given by V out is equal to GM1 times Vn times the total impedance seen at the node between the two amplifiers, which would be 1 over GM7 in parallel with RO1 and parallel with RO3. The 1 over GM6 in this case, this is transistor M6, and looking into a diode we see a 1 over GM like impedance. So if I were to analyze the voltage gain, noting that this GM term is likely to dominate the gain, I would have a VO over VI is equal to GM1 divided by GM6. Now GM1 is just the little gm of the input transistor M1 or M3. And so what we have here is a gain that's equal to minus GM1 over GM7 at high frequencies. So if we were to plot a Bode plot of this response, it would look something like the following. We're just looking at the magnitude right now. The low frequency gain would be what we calculated earlier. We would hit the dominant pole, omega P1. The gain would then hit a 0 and would be equal to minus GM1 over GM6. And then it would hit the second pole frequency and roll off further. Now, as we noted before, this is very problematic for an amplifier because the right half plane zero causes negative phase shift. And you can also see that it keeps the gain above unity. And so we have potential for instability. So in the next slides, we're going to deal with that zero using a couple of different compensation capacitances for the zero. And we'll learn about those next.